Hello friends, we all know that when a substance is heated, um, all the type of substances expands on heating. More or less it depends upon the nature of the material. So when heat is supplied to the material, there is a um, minimum expansion takes place, and when heat is removed from the material, there is a contraction of the dimension of the material takes place. So when material expands in lengthwise or sidewise or in volume wise, the change in the dimension of the material is known as thermal expansion. That means that due to the application of heat, the dimension of the material changes. Therefore, we can say it as thermal expansion. The expansion in length is called linear expansion. The expansion in area is called area expansion or superficial expansion. And the expansion in volume is called volume expansion. If a material is in the form of rod or wire or string, then on application of heat, the change in dimension is along lengthwise. There is also expansion along sidewise, but the sidewise expansion is negligible compared to the increase in length of the rod or string or scale type materials. So therefore we consider only the increase in length, and sidewise expansion is neglected. So there is a change in length now. If the original length of the rod is L, then we can say the increase in length is equal to dl or delta L due to the small increase in temperature. As the temperature increases, expansion takes place. So change in length independent upon the change in temperature. Therefore, delta L is the increase in length with respect to the increase in temperature, that is delta T. So change in length or increase in length of the material depends totally on the nature of the material, what type of material it is. So ratio of change in length to the original length of the rod or string or wire is directly proportional to the change in temperature or increase in temperature. So that proportion so the proportionality constant is called the coefficient of linear expression. This can be represented as so from this expression we can write a relation between original length and new length. So if L1 is the original length at temperature T1 and L2 is the new length obtained at temperature T2, that means temperature increases from T1 to T2, then change in temperature delta T can be written as T2 minus T1, and change in length can be written as L2 minus L1, that means new length minus original length divided by original length. So on simplification we can write this step, and the expression of new length is equal to original length 1 plus alpha, that is coefficient of linear expansion difference in temperature. So once we have this relation, if we are given coefficient of linear expansion of the material, increase in temperature and original length, we can find out what is the new length of the given material, or we can find out the change in length or increase in length due to the increase in temperature. So delta L is the increase in temperature length of the material, and delta T is the increase in temperature, we can say. Or we can say delta L is the decrease in temperature result due to the decreasing decreasing length due to the decrease in temperature. As we know that while decreasing the temperature, material contracted, so the length of the rod or string decreases. So this is the relation between change in temperature with respect to change in length. Okay. Similarly, fractional change in area and fractional change in volume can also be obtained by simplification or simple derivation. Let us do for fractional change in area or superficial expansion. Let us consider a rectangular sheet of a length A and breadth B. So let us see what happens when we increase the temperature of the rectangular sheet. So due to the application of heat or increase in temperature, the length of the rectangular sheet increases. Okay, so the new length will be like this. It is up to here. Okay, this is the new length. So this is the new length, but a whole length is increased with B. Okay, so whole length is increased with the breadth of the sheet, not only side, this side only, but breadth wise the length of the sheet increases. Therefore we can write it as B delta A. That means the product of increase in length times B. This is the increase in length due to increase in temperature or application of heat. So it is, this side also get increases. Therefore we get new area along lengthwise. So B multiplied by delta A is the increase in area along lengthwise. Similarly, with the same increase in temperature, the breadth of the rectangular sheet also increases. Breadth of the rectangular sheet also increases by delta B. Okay, and this increase in breadth is along lengthwise. Therefore the increase in area is equal to A times delta B. That means breadth increases by delta B along lengthwise, so it is A delta B. So this is another increase in area, and in total what happens, this additive effects takes place. Okay, so as the length increases as well as breadth increases, this extra area get added to the rectangular sheet. This is the extra area get added to the rectangular sheet. That is what, due to change in length delta A and due to change in breadth delta B. So new area we get, it is delta A multiplied by delta B. So it is the new area get added. Okay, so delta A multiplied by B, here A multiplied by delta B, and this is the new area, that is delta A multiplied by delta B. So in total or in sum is equal to what? Area of three portions, that is this one, change in area, it is A1, it is change in area, it is delta A2, and the another this delta A3 equal delta A by delta B. So total change in area of the sheet, so total change in area of the rectangular sheet rectangular sheet is equal to delta A1, this portion plus delta A2, this portion, plus delta A3, this portion. So all the three new areas get added to give total change in area of the rectangular sheet. Now we will put this value, okay, A delta B, B delta A, and product of delta A delta B, that is change in length, change in breadth. So it gives an area. So on putting this, we have equation. So on simplification, we have the expression change in area is equal to alpha, that is coefficient of linear expansion, multiplied by area of the rectangular sheet, to the change in temperature, and twice 2 plus alpha delta T. On writing the ratio of fractional change in area, that is delta A by A, to the change in temperature, we have expression twice alpha plus alpha square delta T. But the coefficient of linear expansion is a very small quantity. If we square this coefficient of linear expansion, we get further a small quantity, and the product of that quantity with temperature is very small, so we can neglect alpha square delta T expression, and thus we have change in fractional change in area and change in temperature is equal to twice coefficient of linear expansion. This fractional change in area multiplied by reciprocal of change in temperature is represented by beta, which is called coefficient of area expansion. We named it as coefficient of area expansion. Thus we get coefficient of area expansion is equal to twice coefficient of linear expansion. So this is the relation between coefficient of area expansion and coefficient of linear expansion. Thus we have one relation, that is beta is equal to twice alpha. Okay. So similarly, we can find out the relation between coefficient of volume expansion to the coefficient of linear expansion. To study the expansion of volume of a material, so we will consider a cube of length L. So the length increases equally in all dimensions when temperature increases by delta T. So change in length delta L is equal to the product of coefficient of linear expansion to the original length and to the change in temperature. So we have delta L is equal to alpha L delta T. Now to obtain the expression for volume, we know that volume of a cube is equal to L cube. That means side of the cube to the power 3. So we will cube the length in terms of coefficient of linear expansion as well as original length and change in temperature. So delta L will be, or delta change in volume will be, so we have change in volume is equal to the expression of L plus delta L. So it is expanded as the expression of A plus B whole cube. It is A cube plus 3A square B plus 3A B whole square plus B cube minus L cube. So it is delta L cube. Now we will neglect these terms. There's 3L delta L square and delta L cube, because this delta L change in length is very small, and if we square or cube the change in length value, we will get further small value. So this can be neglected, therefore we will neglect these two terms from this expression. So therefore delta V will be 3L square delta L. So if we multiply and divided this expression by L, we will get 3L cube delta L by L. So we can write it as change in volume is equal to 3V. L cube is equal to volume of the cube. So 3V. V is the original volume. Delta L, change in length divided by original length of the side of a cube. So we have expression 3V delta L by L. And again, delta L by L is the fractional change in length. So we can write delta V is equal to 3V coefficient of linear expansion to the change in length. So in place of fractional change in length, we can write product of coefficient of linear expansion to the change in length. Therefore, from this expression, we can write that is delta V by V multiplied by reciprocal of change in length is equal to 3 alpha. So this whole expression can be said as coefficient of volume expansion. And can be denoted by gamma. Gamma is the coefficient of volume expansion. So gamma is equal to delta V by V. That is fractional change in volume to the multiplied by reciprocal of temperature. Change in temperature is equal to 3 alpha. So we have gamma is equal to 3 alpha. So now we have coefficient of volume expansion is equal to 3 times coefficient of linear expansion. So we have two expressions now. Gamma is equal to 3 alpha, that is coefficient of volume expansion, and beta is equal to twice alpha. So it is the coefficient of area expansion. So these two are important relations, and if we know coefficient of any of the type of expansion, we can find out the values of another quantities of the material.